Geometric sequences. A geometric sequence is a sequence of the form: first term is a, second term is a times some number r, third term is a times some number r squared, etc. So r is what we call the common ratio, and it is what we are multiplying each term by to get the next term. So a times r is ar times r is ar squared, etc. So it's like an arithmetic sequence, except that we are multiplying by the same number instead of adding the same number to each term. Now, as an example of a geometric sequence, let's take a look at the following here. So they occur naturally. Suppose a ball has elasticity such that when it is dropped, it bounces up 1/3 of the distance it has fallen. So if the ball has been dropped from a height of 2 meters, then when it bounces, it's going to bounce to a height of 2 times 1/3, which is 2/3 of a meter. So you can see that illustrated here. We drop the ball, it bounces, but it only bounces 1/3 of the height that it came from. So 1/3 of 2 meters is 2/3 meter. Then it falls again, and it bounces once again, and this time it will go from a height of 2/3 meter, bouncing up to a height of 1/3 times 2/3, which is 2/9, etc. So if you look at hn as a sequence of numbers after the nth bounce, it is given by the formula that you see here. So h of n, or hn, is equal to 2/3 times 1/3 to the n minus 1, right? And so again, if n equals 1, the first bounce, the height after that first bounce will be 2/3 times 1/3 to the 1 minus 1, which is 2/3 times, this is 1/3 to the 0, which cancels out, so it's just 2/3. After the second bounce, we have h2 equals 2/3 times 1/3 to the 2 minus 1. This is 2/3 times 1/3, which is 2/9, and it goes on from there. So here's another example. Suppose we have a geometric sequence where the first term is 3 and r is equal to 2, and we want to find the nth term for that sequence. So let's recall back here in our definition, the nth term of a geometric sequence is given by the first term a multiplied by the common ratio r raised to the n minus 1 power. So back to this example, if a equals 3 and r equals 2, we're just going to plug that into the formula. an equals a times r to the n minus 1. And so this is going to be 3 times 2 to the n minus 1 power. And that's what you see here. Now, technically, the 2 does not have to be in parentheses, but to be safe, it is actually a good idea to write it this way, as opposed to using a dot here. And then the first few terms of that sequence, well, again, to get the terms, you just start with the first term, which is 3, multiply it by 2, you get 6, multiply 6 by 2, you get 12, multiply 12 by 2, you get 24, etc. For the next one, we have a sequence where we can see the first 5 terms are 2, -10, 50, -250, and 1250. Clearly, the first term of this geometric sequence is 2. We can see that. Now, to get r, we have to think, what number are we multiplying 2 by to get -10? And this is not too hard to see that we are multiplying by -5. To go from -10 to +50, we are once again multiplying by -5. To go from 50 to -250, we are multiplying by -5, etc. And so every time we are multiplying by the same number to get the next term. So the nth term of the sequence, again, is just going to be using this formula right here. And it is the first term, which is 2, multiplied by the common ratio, -5, raised to the n minus 1 power. In our next example, we have the sequence 1, 1/3, 1/9, 1/27, etc. This is also a geometric sequence. The first term is clearly 1. Now, r in this case is a fraction. It's 1/3 because the number we have to multiply 1 by to get 1/3 is clearly 1/3. We have to multiply 1/3 by 1/3 again to get 1/9, and by 1/3 again to get 1/27. So every time we are multiplying by 1/3, and this is why r is equal to 1/3. Couple that with a equals 1, and we have the nth term looks like this. And this can actually be simplified to just be written as 1/3 to the n minus 1, right? Because the 1 here isn't really contributing anything. And for the last one, we have the graph of a geometric sequence defined by an equals 1/5 times 2 to the n minus 1 is shown here. So if you find the first several terms of this geometric sequence, you would see that the pattern of the graph would look something like this. And what you should notice is that this graph looks very much like an exponential function. And that's because that's exactly what it is. So geometric sequences are just exponential functions, whereas in the previous section, arithmetic sequences were linear functions. So now we'll just complete some further examples here. So here we have the first 4 terms of a geometric sequence. We want to find the common ratio, the first term and the nth term, and then the 8th term. Okay, so first of all, we'll just notice that the first term of this geometric sequence is 5. Now, to get the common ratio, you can think about what do I have to multiply 5 by to get 15, and that's clearly 3. Likewise, 15 times 3 is 45. 45 times 3 is 135. But sometimes you may not be able to see it so obviously. So another way to get r is to divide any 2 successive terms, dividing the latter term by the former term. So in other words, I can do 15 divided by 5. That would be equal to 3. I can also find r by dividing 45 by 15. That would also be 3, right? I can do 135 divided by 45, and this would also be 3. So no matter how you find it, r in this case is 3. Now the formula is an equals a times r to the n minus 1. So this is going to be 5 times 3 to the n minus 1 power. So that is our an. And then to get the 8th term, that would simply be a8. And that is 5 times 3 to the 8 minus 1, which is 5 times 3 to the 7th power. Now, the terms of a geometric sequence can get really big really fast. And so for something like this, you might need to bring in a calculator to help you calculate the value. So if you go to a calculator and you do 3 to the 7th power, you'll find that that is equal to 2,187. So this is 5 times 2,187. And then multiplying, multiplying by 5, we get 10,935. And so this is the 8th term. And so again, as you can see, a geometric sequence grows really, really fast, especially or only when really the base, right, the r, the common ratio, is greater than 1. So here we have the third term of a geometric sequence is 63 divided by 4, and the 6th term is 1,701 divided by 32. Find the 5th term. Okay, so what we know here, let's write down what we know. We know the third term, a3, is 63 divided by 4, and we know the 6th term, a6, is 1,701 divided by 32. But we also know that a3 is equal to a times r to the 3 minus 1, which is ar squared. And we know a6 is equal to ar to the 6 minus 1, which is ar to the 5th. So now I'm just going to plug in 63 over 4 into a3, and this number into a6, and that's going to tell us that 63 divided by 4 equals ar squared, and 1,701 divided by 32 is equal to AR to the fifth. And now to solve for A and R, what we need to do is just solve for A in each of these equations. So A here will be 63 divided by 4R squared. So I'm just dividing by R squared on both sides. And then here, A will be 1,701 divided by 32R to the fifth. And then these have to be equal to each other because they both represent A, the first term. So 63 must be equal to 4R squared. 63 divided by 4R squared must be equal to 1,701 divided by 32R to the fifth. And now what we can do is we can multiply both sides by 32R to the fifth. And then what happens here is these cancel out. And then right here, R squared goes into R to the fifth, R cubed times, and 4 goes into 32, 8 times. And so we're left with 8 times 63 times R cubed. All right, so we just need to do 8 times 63, and then R cubed, that's going to be 504. R cubed is equal to 1,701. Now I'm going to divide by 504, and so I should say that when doing this, a calculator is, of course, very helpful. So 1701 divided by 504 is 3.375. Now, if you write that as an actual fraction, you're going to get 27 over 8. And so R will just be the cube root of 27 over 8, which of course is 3 over 2. So it's a little bit tedious, but with a little algebra, we can solve for R. And then once we know that R is 3 over 2, we can take this value and come back up here and substitute it. So we have 63 divided by 4 equals A times 3/2 squared. So 63 divided by 4 is equal to 9A over 4. And then multiplying both sides by 4 over 9, we can solve for A. And A is going to be 7. So A equals 7, R equals 3/2. So the nth term will be 7 times 3/2 to the n minus 1. And that is not exactly what they wanted. They wanted the fifth term. But once we have the nth term, now to find the fifth term, we can just plug in n equals 5. And so this is going to be 7 times 3/2 to the fourth power. This is 7 times 81 divided by 16. And 7 times 81 over 16. 7 times 81 is 567 over 16. And this is the fifth term. We can also look at partial sums of a geometric sequence. And so if you take the terms of a geometric sequence, the first n terms to be exact, we can add those up. And it turns out that when you add up these terms, you get the following formula. So the sum of the first n terms of a geometric sequence is equal to a times 1 minus r to the n divided by 1 minus r. And I actually prefer to write this formula like this. A times 1 minus r to the n all on top, and then 1 minus r in the denominator. Okay, but that's just me. I prefer to write it that way. So in our first example here, we are finding the sum of the series you see here. We can see that the first term of this is 1. The common ratio r is 4, right? Because we are multiplying by 4 to get from one number to the next. The big question is, what is the value of n? How many terms are we adding up? We need that in order to use our formula here, which remember I prefer using this formula. So how many terms are we adding up? Well, we know that an equals ar to the n minus 1. And the nth term, the last term here, is 4,096. And that's going to be equal to a, which is 1, times 4 to the n minus 1. And so now we just need to solve for the value of n here. So 4096 is equal to 4 to the n minus 1 power. Now you can figure this out sometimes just by looking at it. Some people might know the power of 4 that gives us this number. But if not, we can take a natural log of both sides. And then we can use properties of logarithms to bring down the n minus 1 power. Then we can divide both sides by natural log of 4. That will cancel this out. And we get n minus 1 is equal to the natural log of 4096 divided by the natural log of 4. And then I can just add 1 to both sides, and that will give us n by itself. So now let's just plug this into a calculator. We have the natural log of 4096 divided by the natural log of 4, and that value is actually 6, and 6 plus 1 is 7. Okay, so n is equal to 7, and now to find the sum, I'm just going to come back up to my formula here, and I'm going to plug everything in. So we have the sum of the first 7 terms here is going to be equal to a, which is 1, times 1 minus r, which is 4, to the n, which is 7, divided by 1 minus 4. This is going to be 1 minus 4 to the 7th power. So, of course, 4 to the 7th power is 16,384, and that's divided by negative 3. And so that's negative 16,383 divided by negative 3. And so if we divide that, we're going to get 5,461. And this is the sum of the terms that you see here. This problem here is essentially the same thing. It's just written in summation notation. And so if I plug in k equals 1, notice that 1 minus 1 is 0, and negative 2/3 to the 0 is 1. So we just get 7. If we let k equal 2, we're going to have plus 7 times negative 2/3 to the 1. K equals 3, we're going to have 7 times negative 2/3 to the 2, etc. All the way up to the last term. And of course, the last term would be 7 times negative 2/3 to the 6 minus 1, which is the 5th power. So here the first term is clearly 7. The common ratio is negative 2/3. Now, the number of terms, we don't have to solve for that here. The number of terms is 6 terms, because we're going from k equals 1 to k equals 6. Okay? So now the sum here is going to be a times 1 minus r to the n divided by 1 minus r, which is 7 times 1 minus negative 2/3 to the n, which is 6, all divided by 1 minus negative 2/3. And now we just need to simplify this answer. So this is 7 times 1 minus, now negative 2 to the 6th power is 64, and then 3 to the 6th power, right? So 3 times 3 is 9, 9 times 3 is 27. If you keep on multiplying, you get 729. And then in the bottom here, you have 5/3, right? Because that's just 1 plus 2/3. So this is equal to 7 times 1 minus 64 over 729 multiplied by 3 over 5. So I'm just multiplying by the reciprocal here. And this is equal to 7 times, so a couple different ways to do this. I'm just going to get a common denominator, so 729 over 729, that's equal to 1, minus 64 over 729, and then times 3/5. And then if we do the math here, 729 minus 64 is 665 over 729, and that's times 3/5. And then we can do a little bit of canceling here. So 5 goes into 665 133 times, and 3 goes into 729. If we divide that out, we're going to get 243. So this is equal to 7 times 133 divided by 243. And from there, if we multiply 7 times 133, we're going to have 931 over 243. And that, I believe, is a reduced fraction. And that's the sum of this geometric series. Now, what about an infinite series? So an infinite series in general is when you have the sum of some ak from k equals 1 to infinity. And so this looks like a1 plus a2 plus a3 plus a4 plus ... forever. Can we find the sum of an infinite series? So can you possibly add up infinitely many numbers and actually get a number? The answer is yes in some instances and no in other instances. So one situation where we can add up the sum of an infinite series is when we have a geometric series in certain conditions. So let's take a look at the example we have here. We want to find the sum, k equals 1 to infinity, of 1 divided by 2 to the k power. If you plug in k equals 1, k equals 2, etc., you see that you get these terms. Now I want to think about this intuitively. Suppose you have a pie and you eat half of the pie. So you've eaten this much of the pie. And then a little later on, you eat half of what remains. So what remains is right here. And now we're going to eat half of that. And half of a half is a fourth. So now we've eaten 1/2 of the pie plus 1/4 of the pie. And then a little later, you have this little piece left over now, and you're going to eat half of that. And you're always eating half because you don't want to eat the whole thing. So half of what remains, which is, of course, 1/4 right here, half of 1/4 is 1/8. So now we've eaten 1/2 plus 1/4 plus 1/8. And if we keep doing this, the next piece is going to be half of 1/8, which is 1/16. And then half of that is 1/32. And so the geometric series that you get here is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64, and this goes on forever. Well, the sum of this, if you were to do this forever, it should be pretty clear that the sum is going to be 1. Because eventually, you're going to eat half of what remains, and you're going to eventually get so close to eating the whole pie that the sum is, for all intents and purposes, going to be equal to 1, because it's going to be so close to eating the whole pie that you might as well just call it 1. So we can add up the terms of an infinite geometric series as long as the value of the common ratio is some number between 1 and -1. Okay, now we won't get into the reasons here in this video, but this is when you can take that sum. So let's summarize. So if the absolute value of your common ratio is less than 1, which is the same thing as saying r is in between -1 and +1, then the sum from k equals 1 to infinity of ar to the k minus 1, which is equal to this, it's just the sum of the terms of a geometric series, converges, so it means that it has a sum, and that sum is equal to this formula, a divided by 1 minus r. Now, if your number r is not in between 1 and -1, so that means if the absolute value r is greater than or equal to 1, then the series diverges, which means it has no sum. So it only converges if the value of r is between 1 and -1. And when it is, this is the formula. And notice that this formula is actually much simpler than the last formula. So in our first example here, we have the sum of a couple of infinite series. We want to determine whether it converges, and if it does converge, we want to find the sum. So in our first series here, we have a first term, which is equal to 2, and our common ratio is 1/5, right? Because 2 times 1/5 is 2/5. 2/5 times 1/5 is 2 over 25, etc. So since 1/5 is a number in between 1 and -1, right? So the absolute value of 1/5 is indeed less than 1. That's true. We know the sum of this geometric series has to be 2 divided by 1 minus 1/5. So again, that's just a divided by 1 minus r. And this is 2 divided by 4/5, which is equal to 2 times 5 divided by 4, which simplifies to 5 over 2. For part B, we also have a geometric series. In this case, a is 1, and your common ratio is 7/5. But the absolute value of 7/5 is not less than 1. It's greater than or equal to 1. Therefore, there is no sum, okay? Or we say it diverges, okay? So we cannot use this formula to find the sum if the absolute value of r is greater than or equal to 1. And that concludes this video lesson.